So this isn't Motorola assembler, it's the assembler that goes with the textbook. Comments start with the period, so we can ignore the first 3 lines, and then there's a blank line, and then we hit the start directive, which initiates everything. So we have prog start 0. So we want to do this in 2 passes, the first pass, the second pass. Start is the assembler directive that marks the beginning of the program. So what does the 0 mean? What is the meaning of start 0?
Address 0.
Address 0, but it means something additional. What does it mean? Yes?
It's relocatable?
Relocatable. So we're going to go ahead and process this as if starting at 0, but that means that the program is relocatable. If we had anything other than 0, that would be hard-coded addresses. Okay, base delta. What does that mean? Base delta.
Base starts at something.
What?
The base starts at something.
Okay, kind of. This means, 1, it turns on base relative mode. It enables or makes it possible for you to assemble using base relative mode. So, does everybody remember the difference between base and PC relative? Base versus PC relative. Anybody? All right. Most of you had CS530 here at SDSU, and you probably had Motorola assembler, and you probably did hand translation to assembler, and then once you're finished, you forgot it as fast as you could, right? Okay, so the question then, or what this is about, suppose we have LDA alpha. So the question is, how are we going to encode that? The CPU knows what LDA is, that instruction, but it doesn't know what alpha is. Alpha is a user-defined symbol. Alpha is an address, right? So what this is a memory reference. So we have to encode this memory reference. So there's really 2 ways to do this. Way number 1 is we encode the full 24-bit address of alpha in our instruction. We could do that. The problem with doing that is that if it's relocatable code, and this is, then we don't know what the address of alpha will be at runtime. Okay, so we will see more about this in a minute. We're going to actually do the encoding. But base delta turns on base mode and sets delta as the address to use for base mode. Now with format 3 instructions, we have an offset, and the available range for this offset is minus 2048 to 2047. So this is the range for offset. So there's a problem here. If we're not encoding the actual address, but we want to do an offset, it has to be in range, and it might be out of range. So we'll have to keep that in mind as we go forward. All right, so the very first instruction is what? What's the first assembly language instruction? What is it? Not the start, that's a assembler directive. I mean, that will translate to machine code.
LDB.
The LDB, yep. Now what's the address of the LDB? 0. That's where you start, right? So let's do this, address 0 LDB # delta. Okay. Now, of course, we can't encode this yet because we haven't found delta. We don't know where delta is. So there's no way we could encode this instruction right now. So we're not going to even try with pass 1. Our first thing is we're going to define all of our symbols. So now we have LDA, X1000. And what's the address of that instruction?
3.
3. Yeah, so we can do 3. All right. Now we have LDA alpha. So I used LDA because the opcode 00, just to make this easier. Okay, what's the address of LDA alpha? What's the address of that instruction? 6. Now, does everybody know why it's 6? Does everybody know why it's 6?
Why is it
No.
6?
Why is it 6? What is the size of that instruction? So, you will have one of these sheets on your test, which you're going to have to do this on the test. I'm telling you right now. You are going to have this. So I'm going to attach to the back of your test this sheet. And this exactly matches the appendix in the back of the text with the opcodes. So these are SIC and SIC XE instructions. All right, so there are columns here. One is mnemonic, add, F, add R, and clear, and so on. All the instructions. These are the instructions the CPU knows how to execute. Then column 2 is the format. Format 0 is the basic SIC instruction, which we're not going to use. So the format 0s you can just forget about. What you want here is format 3, 4. So your formats are 1, 2, 3, 4, 4. Format 1 is just an opcode, it's 8 bits. So, for instance, norm. If you don't have these, your sheet with you, you should, but I'm going to write this down. Norm. It's format 1. It has no parameters, no arguments, no operands, just norm. And then the machine code is C8. So it's 8 bits. That's number 1. Format number 2 is something like add R. And this is 16 bits. So what you have is the 8-bit opcode. And then 2 4-bit register. So this is add register 1 to register 2. So that's 16 bits. Format 3 is something like LDA. It has a 6-bit opcode. It has flags. NIXDPE. Now, why is this 8 and this 6? Well, opcodes are divisible evenly by 4, which means the last 2 digits of an opcode are always zeros. You have 0, 4, 8, 12, that kind of thing. So, the last 2 digits, or binary bits, for the opcode are used actually for the flag. And That's 12 bits, and then you have a 12-bit displacement. "24 bits is how many bytes? 3. There's 8 bits in a byte, so that's 3 bytes. So all of these guys that are format 3 instructions are 3 bytes in size. Therefore, 3 plus 3 is 6. Now we have format 4 instructions, and these must have a plus in front of the LDA to distinguish. They're just like format 3, except instead of a displacement, we have the actual address. 20-bit address. So that's 32 bits. So those are the 4 sizes: 8, 16, 24, 32 bits. 1, 2, 3, or 4 bytes. So as you go down here, you'll notice the next instruction we have. The next one we have, well, no, further down, is a plus in front of it. It's down a little further. I've got a plus LDA alpha. So that one will take 4. Yes?
That was format 1 through 4.
Yes?
What about format 0?
Format 0 we're going to skip. It's because it goes with the older SIC architecture, which is primitive. You have an opcode and a 15-bit address, and that's all you have for that format. So you can pretend that format 0 doesn't even exist. It makes it easier, not harder. Just skip it. So if you're looking on the instructions sheet, you'll see like add space in 034. By the way, you know how to read this signature, right? Let's talk about it a second. So the mnemonic is add space M. M is a memory location. So then the effect, the register A gets A plus, that memory location. So that adds whatever that memory location is to register A. That's the accumulator. Are we good so far? All right. So now, the next instruction after the LDA alpha is LDA eta. Now, what is the address of LDA eta? 9, because it's format 3. LDA, it's all 3s and 4s. All right, what's the address of the next line? I didn't even read it off, but you can give me the address size. Yes? Okay. And that is alpha comma x. LD alpha comma x. Okay, now we have LDA eta x. So I'm trying to get you to see different addressing modes here. Interesting, you'll see the difference when you get down to it. What's the address of this one? Yeah. See, this isn't so hard as you thought, is it? Okay, now I have plus LDA alpha. So this is the format 4 instruction. What's this address? One, 3. No. Why isn't it 1, 3?
Just taking the size of the instruction before.
Yeah. Yeah, it's an easy mistake to make. That's why I'm making a big deal out of it. This is 15 plus how much room this instruction. See, this instruction starts at F. So this scenario here, you've got the instruction here, LDA, whatever. That's this instruction right here. And it starts at F. Therefore, the start of the next instruction after that is how many more? It's 3 more. So this is 1, 2. Now this instruction is a plus LDA, and it's going to take 4 bytes. So the next instruction is going to be what? 16. 16.
1, 6.
Okay. You see that? So it determines the plus affects the next instruction. Okay, so we can write down the address of the next value here. Okay. And the next one is plus LDA. All right. So what's the address on the following? 1A. And that one is LDA at alpha. Okay, so that is 1A. And now I have L3A at Beta. And what's the address of that? Plus 3 or plus 4? Plus 3. Okay. A 10 plus 3 is 13, 1D. Okay, and now I have plus LDA at alpha. Okay, and the address of that instruction? Good. And the last one, LDA, pound sign. So the address of that one is this, because of the plus. Okay, now we have alpha. Reserve word 1000. And then I have delta word 20. Now I have zeta light. And finally I have theta word 10. And then we hit the end. All right, what's the address of alpha? 27. Okay. Well, what's the address of delta? Nope. So the question here is, what can you resolve in pass one? Well, the goal was to discover all of the user-defined symbols and define them. So now we've got alpha, and we have defined it. The value of alpha is what? 2.7. Why do we need to? Well, when we come over here and we have LDA alpha, we have to know what alpha is. Well, alpha is its address, it's 2.7. So that's pass one. We make our symbol table, and we have alpha, and it is equal to. All right. So what is the value of delta? 2.7 plus 3,000. Yeah, we got reserve word, 1,000 of them. Well, 1,000 words is 3,000 bytes. Okay, so to make your life a little bit easier, I will tell you that VB8 is equal to 3,000. Okay, 16. Okay, so what's the address of delta? Eight, 7. B and 2. D. D, E, F. So delta now, delta is okay. Now then, what's the address of zeta? What is the value of zeta? DDF plus how much? How many bytes are alphabet here? Yes? 3 bytes, right? A word is 3 bytes. Okay. Is that right? Yes.
What's the difference between word and reserve word?
Well, reserve word reserves 1,000 words of storage and it's uninitialized. However, word declares a constant, which is 3 bytes and puts a 20 in decimal. So, B, E, 2. Now, what is the address of Ada? Ada? Address of Ada. 3. Where did 3 come from? E, O, F. How much space does that take? 1 for each character. And there are 3 characters. So we have. Now don't get confused with this byte declaration. We haven't done a whole lot with this. But understand that there's 2 forms. C, E, O, F. C stands for character. So you put them in E, and O, and an F. Now then, the other form is this. How many bytes does that take? I'll give you a hint, it's not 4. So what's the X stand for? Hexadecimal. That's 2 bytes. 2 bytes. FF, FE. That's 2 bytes, 16 bits. Notice that your characters, ASCII characters, each character takes 2 hex digits. Each character takes 2 hex digits. So this is actually bytes. 4, 5, 4F, 4, 6. Now A is 41, and B is 42, and C is 43, and so on. Questions? Are we good?
I don't get that.
This is the hexadecimal value, and this gives you 2 bytes, 1 word in memory. FF. Numbers. Numbers. What I suppose is confusing is this E is 45. But it's not going to put an E in memory, it's going to put 45. O for F, F for 6. So each character takes 1 byte. But 1 byte is 2 hex digits when we're talking numbers. Does everybody understand? Are you confused about this? How many bits are in a byte? Everybody familiar with this? 8 bits in a byte. Okay. So, if we have an 8-bit byte, let's just make one up here. We have an 8-bit byte. What is that in hex? Yes, each 4 bits is 1 digit. That's 8 bits. It's 2 digits. Okay. A 16-bit value, how many hex digits does it take? 4. Why? 4 times 4 is 16. It takes 2 hex digits per byte. 2. Therefore, it takes 1 byte. Takes 2 bytes because it's a character, an F and an E. Everybody okay with this? The ASCII codes is 1 byte for each character. So this is 4, 5, 4, 6. Remember, these are 2 bytes. This, however, in memory is 1 byte because it's a number of characters. Everybody understands there's a difference between 123 in quotes versus 123. Yeah. How many bytes does it take for this? 3. What's it look like? There's 1, 30. Those are the ASCII characters. 4, 1, 2, 3. It's not an integer. Yes, an integer. This is 7 times 16 plus 11 is 123. So it's really pretty easy. Characters, it takes 1 byte for each character. Hexadecimal, integers, it takes 2 integers to make 1 byte, 2 numbers to So, how many bytes? 4. It takes 4 bytes, there's 4 characters. Everybody good? Two. All right, you guys got it. That's not the label. You cannot have an odd number, no. That's now 4. Number. Well, some of them are like, I feel all of that out and all over the place. Okay. It's a little bit. Okay, so pass 1. We give an address for every line of code. Okay, we did that. And we define all of the values that are given. So we did zeta and we didn't do eta. What is the value of eta? Yes? Everybody comfortable with this? All right. Now then, let me throw a monkey wrench in the works. Imagine here that I have all right, so we've added one more. We've got food. Usually define symbol, certainly not machine instruction. What's the address of food? 0. What's the value of food? What do I want to put here? 8. Okay, why 8? That's what EQU means. Equate equals to. So the EQU allows you to manually set the value of a symbol in your program. That's what it's for. That's its purpose. Questions? So this is what happens on pass 1. You get the address of everything, and you build your symbol table. Questions? Anybody? Okay. So now we got pass 2. The fun begins. Now pass 2. Pass 2, we're going to generate all the machine code. Okay, so I'm going to add another column here, and we're going to do the machine code. So, LDB. Well, I've got my little cheat sheet right here. So let's see here. Get some scratch. LDB. So this is a format 3.4 instruction. Format 3 can then have a plus in front of it. And LDB is 6.8. 6.8. So, now then, we have base delta. So we've got LDB pound sign delta. So now I want to build this instruction. That's the output. So I have the last 2 digits, the 0, these are actually the beginning of the flags. We only really needed 6 bits here, because they always end in 0, 0. So, this is the end bit, this is I, so I have N, I, X, P, D, and E, they're my 6 bits. All right, what does the N stand for? in. These are flags. This is an addressing mode. What's in? Indirect. Indirect like this one. At alpha. What does that mean, indirect? Have you forgotten? Indirect. What that means is in memory, at location alpha is an address that you use to get the value. It's a pointer. What's the difference between int p and int star? One's an address, a pointer, one's a value. Okay. Well, how does that relate to this image? This is the pointer. It's a pointer, not a value. You go to alpha, there's an address. That's just like p, pointer p that holds an address where the actual value is. Does that make sense? You with me? So it's a pointer. Okay. So is the addressing mode indirect? Is it indirect? No, it's not indirect. Okay. Is it immediate? I for immediate. Now what's meant by immediate? What does that actually mean? Right this very second? Do it immediately? What does immediate mean? It's a constant. It's kind of a strange term, immediate, but it's exactly right, a constant. It's a constant. So if you have a declaration in your program, int x equals 2, is 2 a constant? Sure it is. It's a hard-coded value in your program. Yes, so it's a constant. All right. So in immediate, yes. Now there's a quirk here you need to be aware of. If it's not indirect and not immediate, don't put 0, 0. You put 1. All architectures have these kind of quirks. We will see going forward, we've got more of these to do. All right, X. What's X? Indexed. Indexed. The address plus the value in the indexed register. That's this mode. Do we have that? No, we don't. Yes.
How is this immediate?
Pound sign delta is immediate. Pound sign delta is an immediate value. It's a constant. Well, what is pound sign delta? What's the constant? 0, 0, BBF. That's the constant. We didn't know what it was till we finished pass 1. We know now, but it's a constant. Okay. Now we've got the B and the P. What the hell are the B and the P? Base or PC relative. Okay, so choices here. I need to encode the address of delta. Now the address of delta is 20 bits. It's 5 hex digits. I don't have room for that. I could use format 4 to do that, but instead of the actual address, I'm going to encode in its place a distance or a displacement. Now then, can we use PC relative mode or can we use base mode? We have to use PC because base isn't set yet. We can't use it until it's set. The base relative mode says go to the base register, take the value in the base register and add that as the displacement. Well, what's in the base register? Nothing. We're loading the base register just now. So until we do this, it's got nothing in it or garbage in it. So we must use PC relative mode. Okay, how does PC relative mode work? Offset, the offset is equal to destination minus source plus P's or program counter. Let me do that. Program counter. So the program counter keeps track of where you're at in the program. It starts at the first address, and as you execute each instruction, you increment the program counter by the size of that instruction. So as you go along, the program counter has 0, then 3, then 6, then 9, then 12, then 15. That's what's in the program counter. So what we want to do is say, okay, from where the program counter is at right now, go forward in bytes and grab that down. So you can rewrite this as destination minus source plus 3. Well, the program counter moves. As soon as we have read this instruction at address 0, the program counter has 3 in it. So now we need to encode LDB, but the program counter's got 3. So the address of this instruction plus 3 will give us the program counter. You with me? The program counter moves. So we can use this address to encode it, but we got to add 3 to it because the program counter will move. So where do we want to go? Delta BDF minus okay. So what's the value here? BC. Okay, what's the problem? What's that? It's too far. You can't do that. What's the problem? Well, let me ask you this. If we're talking about a 3-digit, i.e. 12-bit number, is BCD positive or negative? Negative. How do you know it's negative? It starts with a 1. In binary, it starts with a 1. It's 2's complement. Because you can have backwards memory references. You have branches you need to go backwards. Okay, so this is a backward branch, but we can't go backwards. Uh-oh. What's the problem? The displacement is too big to fit in a 12-bit displacement. Does everybody see the problem? All right, so if you're not familiar with 2's complement, I'm assuming you know that. B is a negative number because it starts with a 1. B, D, C. Starts with a 1, it's negative. Is everybody comfortable with this? Okay. For any given size, if you split it exactly in half, so we're talking 3 bytes here, 12 bits. If you split it exactly in half, then half of them start with a 0 and half of them start with a 1. Would you buy it? Yes? No? With that partition exactly, if you have a set of numbers, you want to divide them in half equally. A set of digits, so we're talking binary. Would you agree that half of them start with 0 and half with 1? Does that make sense to you? Okay. Well, that's what we have here. The ones that start with 1 are negative. All right. So this is not going to work. What do we have to do now? what's the fix? Anyone? There's only one fix. There's only one fix here. Make it format 4. Oh dear, that's our very first instruction. What did it do to all of our addresses? It effed them all up. Excuse my French. They're all wrong. Does everybody see why? All right, so there's this discussion I want to have before the test we talk about this. Having this plus here makes it easier to write the assembler, but real machines don't do. So what's a real machine to do? You start over, and this does happen. As part of the logic is, okay, I guess start over. Yes, so now what do we have to do? This gets to be 4, and this one 7, and this one A, and this one D, and this one 1 O, and this one 1 3, and this one 1 7. And 1B, and 1E, and 2 1, and 2 5, 2 8, D F, E O, 3. Okay, then we have to fix these guys up. 2 8. DF becomes EO. Three. Problem solved. Okay. Now then, it's a format 4, so what are we going to do? Is it base relative? Can't be. Is it PC relative? No, it's format 4. So we set the E bit, and then we put the full address of delta. So we regroup, and we have 6, 9, 1. We have 6, 9, 1. And what's the address of pound sign delta? 0, 0, B, E, O. And then okay, base is now enabled. Base is only forward, not backwards. Okay, continuing on. Let's move to the next one. LDA 1000. So I have different addressing modes here for you to look at. LDA. So the LDA code is 0, 0. So the rest of these are all LDA. So it's 0, 0, and then we have N, I, X, V, P, E, and then the displacement. All right. Is it indirect? The addressing mode, is it indirect? Is it indirect? No, it's not indirect. Is it immediate? Is it immediate? No. How do you know it's not immediate? There's no pound sign. So notice this and this are the same addressing mode. They're different in the sense that this is a constant and this is a symbol, but there's no pound sign. Therefore, it is not the immediate value. Now there's this sheet I gave to you at the beginning of the semester. And this is one of those addressing modes I grayed out at the very top. You guys have this sheet, right? Like the reason I grayed it out is because you wouldn't do this. That is, it's a very unusual instruction. Why? Because you've hard-coded the 1000 here, and who knows what's in memory at 1000? Nevertheless, it's legal. Okay. So it's not immediate, and it's not indirect. So these become 1. Remember, 1 means it's neither. The reason for that, 0, 0 is the original SIC, so it's for backward compatibility. If it's neither one. X, no, there's no X. Base or PC relative. Okay, that's why this differs from the next one. It's the same addressing mode, it's a memory reference. But how in the world could you encode that with a B or a P? What's that? It is. It is. So it can't be encoded with base or PC relative, and it's not extended. And in fact, now we're just going to write 1000, and that is the address. So, okay, what is it? What is the address? So let's see, 1000 in hex. I don't know off the top of my head. That was 3000 divided by 3. Well, let's see. I don't know if I have a calculator. I should have written this down. What's 1000 in hex? Let's see. Somebody's got a calculator. What is it? 3E8. You know, that sounds familiar. 3E8. Okay, that's 256 times 3 plus 14 plus 8. Is that right? Well, let's just say it is. So we can move on. Let's say it is. So we got 0, 3, 0. 3E8. And there it is. Yes.
I don't understand where you put like the address of 1000. I didn't put placement. Isn't this format 3?
Oh, I'm sorry, I put a dollar sign. I meant this. I apologize. Dollar sign next would be too big. I meant 1000, so I apologize for that. I put the dollar sign in front of it too quickly. I meant this. You're right, and 1000 wouldn't fit either, so we'd have to change all the addresses again. But I meant 1000, so we'll go with that. I know there's a dollar sign on your sheet, it's just a typo. All right, the next one, LDA alpha. Okay. LDA alpha. So, it's not indirect and it's not immediate. Everybody's comfortable with what immediate and indirect are. What's indirect? It means if you go there, like this, you will find an address starting at alpha. You go to that address and you reference it. So it's like a pointer. Okay, and they're marked, it has the at sign in front of it. Okay, is there an X? No X. Now then, base or PC relative. Either way works, provided it's in range. So the question is, what should you do? Well, it's up to the assembler to decide, and one is not quicker than the other. But you have two choices. So I would recommend in general that the heuristic be try PC relative first. If that doesn't work, try base. If that doesn't work, throw an exception. So let's try PC relative. So we have destination minus source plus 3. All right, the destination, what we're trying to read is alpha. And that's at 0, 0, 0, 2, 8. I looked it up in my symbol. All right, minus source plus 3. The source is at address 7, plus 3 is 8. We subtract, and what do we get? You guys know how to do this, right? Let's step through it in case you're a little rusty. 8 minus 10, I can't do it, I have got to borrow. So I borrow, this becomes a 1. Cancel it. Yes?
Would it be source plus 4 if there was a plus in front of the instruction?
Yes, it would, but there isn't. Yeah, there would be, but there isn't. Okay, so we get 28 minus 8. Okay, 2 8 minus 10. So we cancel the 2, becomes a 1. We borrow 16 because this is hexadecimal. We already have 8, so 16 and 8 are 24. Yes? Minus 10 is what? Minus 10 is 14. Okay. 1, 0, 0. You can always check your work. 14 and 10 is 24. 24 minus 16 is 8. Carry the 1. Yes. Check your work. Okay. So, we can use PC relative, which means it's not based and it's not extended. So I have 0, 3, 2. 0,